professor at the University of Bonn. I lead the agricultural robotics group, and I'm going to talk to you a little bit about some of the robots that we have and the robotic vision systems that we develop for these systems so they can do useful things in the field. If you're interested about some of the work my group does, you can see the website there, and at the end of this presentation will be my email address and website as well. I'm going to briefly introduce some of the systems that we use in my group. So on the left-hand side over here, we've got 1.1. We're going to talk a little bit about that here today. That's wheat management and also crop monitoring system. You can see it's got a range of different sensors, including GPS, a whole bunch of cameras, and a few other bits and pieces to enable it to do some wheat management actions as well. Closer to me, on the right-hand side over here, you've got Patobot. This is a system that we put in glass houses. So we employ this system to go through and do monitoring and potentially look at what's going on within the glass house field. You can see that runs on the pipe rail systems there, but also comes equipped with a UR5 arm, so we can think about doing things like local sensing and also intervention as well. We do have some other robotic systems, so we've also got a Husky down below that we use to rapidly develop and prototype systems, and you can see in this particular case, it's being deployed within orchards. So we do a range of different work, both in arable farming, glass houses, and orchards. Because we're able to do that at the University of Bonn because we have 180 hectares of arable farming land, as well as glass houses and orchards available to us. At the top is a UAV, so we also have aerial-based vehicles that we go through and deploy, in this case M300, where we're looking at how we can actually rate the efficacy of weeding actions both before and after to understand what's actually going on and if the weeding action we wanted to take was in fact successful. And that's a project funded by the German Ministry of Agriculture. Now, why is vision important? I probably don't need to tell you exactly why vision is important, but vision is really challenging within agriculture. It's important because we want to know how to interact with that environment. We want to know where things are so we can either know how much crop we have, what the actual state of the crop is, or we want to actually do an interaction. We need to know precisely where that is. This is a picture of sweet pepper grown in Gatton in southeast Queensland that I taught many, many years ago with colleagues from QT. I'm going to ask you, because this is what we're asking the robotic vision systems to do, how many green sweet pepper are in that image? Does anyone have a guess? No. Anyone else? Close, 5 is close. There's 6, and that's where they are. And this is what we're asking our robotic vision systems to do, right? This is a really challenging environment because we're doing things in this particular case where we've got green on green. We've got high levels of occlusion from the leaves. We've got these things in the background, the fruit that we really care about, that we want to find, but they're heavily occluded and they're even the same color, right? So this kind of data is really hard to deal with, and this makes it a really exciting area to deploy these kind of different vision systems that we have. Now, in my group, we use color images, of course. We also are big on using the geometric information about the scene, and we do that by capturing depth information. We're not just using that though, okay? And what you're going to see in this presentation is that we're taking the color as well as the depth image. We're also going to take the temporal information into account as well. And it's been said a couple of times, but really emphasizing that what we've got here is a unique opportunity, because what we have in this particular scenario is we have a moving system, we have a robot in the field, and here we have a very static scene. And so we can have an understanding of what our vision systems are able to do and exploit in terms of that information when we deploy them in this somewhat more controlled environment. The first system I'm going to talk to you about today is that 1.1. An important thing when we're deploying 1.1 is that we want to be able to take it in the field, get some data, and do some actions. Now, to do that, we need to actually navigate through the field, and let's be honest, we all go through and joystick them through the field, but what we want them to do is to autonomously navigate. Now, this is a complicated thing because although we've got wonderful GPS, and we have great signal for GPS out in the fields we have, this is not always the case. And even though farmers may have GPS on their particular system, they may not actually do GPS-guided seeding. And this means that there's some variability in where the crop row is in the field. And so for some higher levels of autonomy, what we're looking at doing is things like doing crop row detection and crop row following, so we can deploy it in a range of different environments. And what you see, the environments that we have here. At the top, you've got fava bean, in the middle, you've got lemon balm, and down below here, you've got fairly early germination of sugar beet. So you have really diverse different environments we want to put this system in What we did was develop a system to do crop row navigation in these different environments using effectively the same system to do that. That system consists of about 4 different steps. So the first one is to actually have the system deployed at a particular point. And the very first thing it does is actually looks at the field and decides how many crop row lanes are going to be underneath me, okay? Because this is variable also within the field. So it goes through and segments the image using fairly simple vegetation segmentation and decides based on off transforms how many lines are going to be underneath that particular system. And then the second step is going to follow that. It's going to look for where the center line is and it's going to follow that in stage 2. Gets to the end of the crop row, okay? Detect that it's at the end, and then start switching the number of crop row lanes that it found at the start. And then keep going back down the other end, over and over again. This is non-trivial. As you can see, we've got very different canopy structures here. So actually looking for the different crop row lanes is quite challenging. Also, there is some difference within lanes. You can see on the far right-hand side there that we've actually got a far bin that's outside the crop row line. But we can still handle that. So if you look at how the system actually works, we've got the vegetation segmentation using simple Otsu thresholding. In this case, you could use a range of different techniques, but you use that purely for simplicity. And you can see that we're starting to have a structure within the scene. And this is what we're exploiting, okay? So this will also work for curved lines up to a point, okay? As long as we can assume that there's a straight line that we can follow within that field. Now, once we've got this kind of segmented image, we go through and try and identify different potential plants. And although this may lead to under segmentation, in particular for the front one, we have different techniques to try and ensure that we have a few separate points. Or over segmentation, as you can see with the sugar beet, same thing with the fava bean. Even with that, we can go through and get a pretty good idea of where that structured crop row lane is going to be within the field. Okay, and then we can do some fairly easy line fittings to get through to have the center point, which is our blue line here. What that lets us do is that we've detected the number of crop rows, we're following that center crop row line, and we can go through and deploy that in a range of different environments. So what you're going to see in this video here is a bit of an idea about some of the fields we have at the University of Bonn. This is kind of phenotyping fields that we use for a range of different experiments. And what you're going to see is the system go through in fava bean. It's already part way through, so it's already done the detection of the number of crop row lanes. In this case, it's following the center red line here, going through. Keep in mind, this is somewhat sped up, but it's still real time on the robot in the field doing this. Detecting the end of the lane, and now it's going across. And it's shifting and detecting and trying to classify if it's got a new crop row as it shifts across, okay? And you can do this with fairly simple features, even just if features are sufficient for you to try and actually classify if you've got a new crop row and go through, count the number of times you need to do that, and just keep going down. One of the things that you can see that we've exploited on this particular platform is that it's a robot from Robotics. It's a 4-wheel drive, 4-wheel steer platform. And we've mounted the cameras both front and back, so we can exploit the fact that we don't need to do any turning and just shift across the number of crop rows that we need. Now, the aim of having some of that autonomy is so we can do interesting things, right? And one of the interesting things is in terms of, if you look over here on the left-hand side view, the system has weeding tools. And the particular weeding tools and the way that we've gone about it is a little bit different from prior work. So I also worked on a system for AgBot 2, where we had effectively static systems. And what we're looking at here is actually having dynamic movable systems. And what you see here is that we've got 4 linear actuators that move. So we have guaranteed forward motion from the vehicle, and we move to do precise intervention with these heads. Okay, relatively simple system, but allows you to change and have multiple tools deployed on the same system. We don't just do weed management, we also do crop monitoring, and that's going to be something I'll talk to you in a little bit more detail. What we do is we do instance-based semantic segmentation, and you can get an idea of what that means here for weeds. Okay, you can get an idea that we try and go through and actually estimate the state of the field at any particular time. The systems I'm going to describe to you today, though, are general not just for arable farming, but also for horticulture and glass houses. So we're still doing the exact same semantic segmentation systems also on Parabot. And what I mean by instance-based semantic segmentation is per pixel, what the particular crop or weed is, or plant is in the field. And for the arable farming scenario on the far left-hand side, what you see is a fairly dense weed pressure here, or high weed pressure here, where the crop is actually sugar beet shown in magenta. Okay, so different colors are highlighting the different, in that case, plants. In the middle case, different states of growth or different ripeness stages for sweet pepper. And then you've got the different instances there. And we really want to know where the different instances are, so we can do things like estimate the state of the field, how many crop we have, and whether they're ripe or how large they are. And I'll show you where this has come from shortly. So some of this was initially done as work when I was at Queensland University of Technology. And what we were doing was we developed just a vision system, purely vision system, where what we could do with faster RCN was actually have a parallel layer, so the object detector, and basically say, well, what's the ripeness? And this could be in terms of green, mixed color, breaking color, or actually full color red. And what we were doing was we were then tracking, okay, just assuming that if there was sufficient overlap and we had a high enough frame rate camera, we could just keep tracking what was actually going on in the field and actually do the associations so we can actually count the number of sweet pepper in the field. So what you're going to see in this video is we've got numbers for the crop, and this is literally the number of sweet pepper that we've actually counted so far. The bounding box is the color that we're estimating, so this means the ripeness, of course, ripeness estimation, that means green, mixed color, or red. Okay, and this is a fairly naive system, but it works extremely well, right? You can put this, and as long as you've got a high frame rate camera, you can do this kind of assumption. Now, just to be clear about the kind of assumption that we're talking about, the kind of assumption is something like this. So if we take a frame T in orange over here, and then a frame T plus 1, which is going to be in blue over here, you're going to see that there's some overlap, provided we have a high frame rate camera, but there's also been some shift, right? And so we have to find out the tracking parameters for doing that. So we have different training validation sets to do that before we then deploy the actual system. That was work that I did about 4 years ago while I was still in Australia. More recently, we've been extending this so we can do instance-based semantic segmentation. One example of this is that we use this for mask RCN. Okay, so this provides us with the segmentation mask that we want. And I'm just going to briefly describe this in a little bit more detail. What you see here is that when you consider the standard mask RCN system, you come out and you say, well, I get an object, okay, versus background. And let me give you the example for sweet pepper. Our object is just a pepper. Okay, if you consider it for weeds and crop, our object is just a plant. Okay, and from that plant it produces a mask. And then when we want to do something like species classification or ripeness estimation, we have this subcategory, which is effectively just a parallel layer within the mask RCN to tell us which particular class you think that is, whether that's green, mixed color, red for sweet pepper, or for the different plants, whether that's the crop or the weed in a core sense, all the way down to the fine-grained species classification. So actually saying what plant you think you have in the field, which is actually really invaluable information. The other thing that we do is we exploit the fact that we're on robotic platforms, right? So the previous story I told you before said that we just had a high frame rate camera. We just assumed there was good overlap, frame to frame, kind of like this. But these days what we do is we actually try and reproject. So we've used the geometric structure of the scene, how far we've moved, fairly simple common knowledge here, and actually estimate or predict where we're going to see that in the future so we can do the tracking really accurately. In addition to that, it's not just being able to reproject the mask, it's also being able to look at slightly different representations of what your objects are, so you can do this accurately. For instance, doing this for small objects is actually quite tricky because you'll have very different kind of IOU characteristics for large versus small objects. And so the representation that you use is actually really important as well. Now, if you're able to incorporate all this information, you can do really, really accurate onboard local classification and counting of different plants. And what you see here is in green, you've got the sugar beet. We're going through a field and it's showing what happens when we actually take one bud out and actually do this kind of processing on it. So you can see the different colors of the different plants or weeds. Might be hard to see in this particular room, but what you see here is also there's a number at the top right. So that number is exploiting the fact that we've got a stereo camera to estimate the geometric scene, and we're showing the viewable area of the plant. So now we actually know literally how big that is. Okay, and you can think we're getting multiple viewpoints about it, and how you can use that potential 3D information is also of interest to us. We can then go through and say, well, now we know what kind of plants we have in the field and what kind of action we want to take. This is also really interesting from a weed management perspective because, for instance, if there's certain plants in the field that are non-competitive with the weed, with the crop, you don't need to take an action. Or if it's small enough that once the canopy closes, again, do you really need to take an action? So having this information makes for a cool video, but it's also really important information about how you take an informed action in the field. If you want to change, how do you do that action for what we do these days? And that exact same system also works for sweet pepper. Okay, changing the training data is about the only thing we do. Here we're using in both cases wheel odometry to do the reprojection. You can use other information too. So in the previous example, for instance, we've got GPS, and that helps a lot because the wheel motion leads to some certain interesting characteristics for the tracking motion, and other things. You could also think about doing this post-process with visual odometry. And again, we're estimating the size of the sweet pepper by looking at what's the visual, viewable area of the sweet pepper and providing that. So we have an overall size estimate of what's going on. Now, what else can you do with a system like this? Well, a lot, we think. So if we take something like Patterbot through a glass house and start running this over and over again, we can start to look at the state of the field. We can start to provide representations, like a 3D representation of the field, which is interesting. But from that 3D representation, if we also have the segmentation, instance-based semantic segmentation results, we can also start looking at what the field looks like in terms of the distribution of the crop within the field. So people can get an idea very quickly, very rapidly of what's actually happening in the field. And also if there are certain problem areas where there's actually no crop being produced, for instance. This is also really important in terms of labor deployment. For instance, if you know that you've got sufficient crop that you need to pick, you go through and actually deploy the labor force as you need. Now, what you see in there is kind of a coarse way that I said at the beginning that we incorporate this temporal information. We've looked at other models too, so recurrent neural networks, and exploiting the fact that we've got a relatively static scene and actually doing temporal models. One of the issues with this, of course, is that there's very limited data and it's really hard to actually go through and hand annotate a whole lot of video data to actually get the ground truth labels. So some of the work from a student, Ali Reza, was we can actually exploit the fact even further that we've got a static scene and generate virtual data from that relatively static scene by just cutting up the ground truth images that we have and treating them like sequences, provided we have an idea of what our movement parameters are within that particular scene. And that works quite well, not just for sweet pepper, but also for arable farming for doing sugar beet crop wheat segmentation. Not just that, but also more recently looking at how we can actually incorporate and inject this prior information. So previously when we were doing the tracking, we're taking the output of the network and understanding and trying to incorporate the structure of the scene to do better tracking. The real question here is how do you incorporate that within the neural network to bias it such that you can do even better segmentation based on the prior information and the fact that you've got a relatively static scene. That's some work that's still under review by Klaus Schmidt. We've also done some work in terms of cross-domain. So this is both in terms of cross-domain in terms of the same problem, in this case sweet pepper. You can see we've got sweet pepper data captured in the field in a protected cropping environment in North Queensland. You can see an image over there which is quite different to what you'd see for a glasshouse environment over here, but also in terms of the annotations, right? So sometimes we've got semantic segmentation masks and sometimes we've got bounding boxes. How do we exploit that information and use that across the different domains? That's the work that Christoph Mein and Michael Halstead started at QT and has continued over here at the University of Bonn. So you've seen a range of different ways that the vision systems are really challenging and quite interesting, but we can really exploit the fact that we've got a unique opportunity of a relatively static scene and really incorporate that information to develop quite unique vision systems specialized to agriculture, but also more generally giving an insight as to what's going on with those systems. We do a whole range of other work as well, so I've talked a little bit about the temporal and spatial temporal models we do, and a little bit about how we look at doing things across domains, but also trying to think about how do we have systems that work generally, right? How do we not have to actually annotate more data for that specific environment and get it to work? Recognizing that they may not also work as well, looking at semi-supervised approaches, how do we actually get the least amount of data from a particular field that we want to deploy for, particularly if we're doing a monitoring exercise. This makes more sense, being able to actually post-process that. How do we do that quickly and efficiently? Also, we're on a resource-limited environment. Okay, we want to make the best use of the limited amount of compute and the limited amount of battery that we have. So learning efficient models is really important, and that means learning efficient deep neural networks to be able to be deployed in these environments. And of course, if you think about having a linear system on a robot, we're now talking about how do we actually plan the intervention. Okay, if we're now also thinking that we know the size of the different plants, is there a different priority, the larger or small plants for a particular plant species? How do you plan that intervention in the field in an optimal way? These are some of the other things that we address in my group. So I'd like to thank you all for being here on the Friday afternoon or evening for people overseas. For your attention, there's my email address as well as the website for my group. I look forward to your questions.